Hey everybody. So today we're going to talk about ring buffers. Alright, so ring buffers are pretty fundamental data structures in a lot of systems programming. So we're talking about like packet handling, embedded systems, real-time systems. When you need a quick FIFO data structure that is very efficient, ring buffers can often be a solution. And so we will get into some real world examples of problems that they solve as usual, and then we'll do an implementation after this one, after the video, and an implementation video. So let's get started. All right. So ring buffers, what are they? So they're fixed size data structures that use a circular memory layout to store things. You can kind of envision taking a cue and just wrapping it on itself, right, until the head and the tail touch each other. And so there's two common functionalities with ring buffers: either new data overwrites the oldest data, or insertion is blocked. And that's what our code's going to do. It's going to block the insertion. It is very easy to change it to overwriting. You basically just kind of flip the head and the tail. It's not a big deal. So, I'm not even going to bother implementing one later on. Like if you want to implement an override ring buffer, it's very easy to do. Just look it up. And so, let's talk about an analogy. All right. So a good analogy for ring buffers is if you imagine like a carousel of lockers, right? And then the carousel's got these attributes, right? So it has a fixed number of lockers, and they're arranged in a circle. We take a blue marker to identify head, right? And so this is going to be the locker where we insert the next item, right? And then we have a red marker, tail, to identify where to retrieve the next item. Okay, when the carousel's full, you can't add anything until space is freed by removing old items, right? And then once you reach the end of the carousel, the marker's wrapped around to the beginning, forming this continuous loop. Okay, so the structure. So we define a buffer which has a capacity, and then head, and then tail. And so the buffer is like the lockers. Head marks the position where a new item will be added, and then tail marks the position of the next item to be removed. Okay. Now, the wrapping around behavior is the most important thing when it comes to a ring buffer. Okay. And it's implemented using modular arithmetic. And if you don't know what modular arithmetic is, I'm going to go into it a little bit after this. But it would probably be, in general, it's probably a pretty good idea to just brush up on some number theory. It's not overly complicated mathematics. And so it would be worth your while to go and just, investigate some number theory. There's lots of great books. There's lots of great tutorials. Having a little bit of basic understanding of number theory is good. Now, the wrapping around, okay? So, this ensures that the buffer behaves like a circular queue instead of a regular linear structure like a linked list, right? So in a ring buffer, there's always one unused slot, okay? And then to distinguish between the full and empty states, right? So if we allowed head to have the exact same index as tail after the final insertion, you wouldn't be able to discern full and empty, right? And so what we do instead is mark the buffer as full before inserting the last available index, right? And then this is why our isFull runs its check before our push method inserts a value, right? So here, this is going to be the code we're going to implement to test if the ring buffer is full. So we check if advancing the head would overwrite the tail, right? And if it's true, the buffer is full, and we reject the inception, right? And so you see here, we advance the head, we do a modulo on capacity, and we check if that equals tail, right? And so what this is going to come back with, it's going to be, well, I'm going to save it when we start talking about modulo, okay? And it'll be clear. Now, then in our push, we first check if the ring buffer is full. If it's full, we reject the insertion. If it's not, we insert, right? So we have our buffer. We insert at head some item, and then we advance it, right, to the next available index. Now, what is modulo arithmetic? Okay, so modulo finds the remainder when dividing two numbers. Okay, so 5 modulo 3 is 2, 3 goes into 5 one time, 2 left over. 8 modulo 4 is 0 because 4 equally divides 8, right? There's no remainder. Okay, now, in the ring buffer, so like I said, we use it to do this wraparound thing, right? To detect when we reach the end. Now, self.head plus 1, this is the simulate, this is moving the head forward, right? As if we're about to insert an item. And then if the head reaches the end of the buffer, the capacity, modulo wraps it back to the beginning, the index of 0, right? So that's what the modulo is doing. It's returning an index in the buffer, right? And so this prevents the head from exceeding the buffer size, right? And so the comparison to self.tell, right here, means that if the next head position equals tell, the buffer is full, right? So if this comes back true, it's full. Okay, so look at here, right? So we have A, B, C, and we have a buffer size of 5, so a capacity of 5. We currently have all but one full. Okay, so we have head equals 4 and tell equals 0. All right, so how does that happen? Okay, so down here you'll see. So if another item is inserted, head moves to 0, right? Meaning head plus 1 modulo 5 equals tell, and the buffer's full. And the same thing happens in push and pop. Okay, so think about this, right? So head is 4, okay? And we're doing head plus 1 modulo 5. 5 modulo 5 equals 0, okay? And so that's when we get that index of 0 out of the modulo expression, we know that the buffer's full. Now, let's come down here, right? So this one, so like I said, right? So up here, the self.head, this is the increment, this is incrementing, right? So if we come back up here to our push, we'll see here, we have our buffer, we insert some item, and the head is the currently available slot, right? So self.buffer, the available slot in the buffer, we're inserting an item, and then we're advancing to the next index when we want to insert something, okay? Right? And so, like I said, this increments head by 1, moving it to the next slot for insertion, and modulo is applied if the wraparound is needed, okay? So right here, we have head is at index 2, right? We don't have anything in 3 or 4. So after inserting an item in index 2, we get self.head equals 2 plus 1 modulo 5 equals 3. I explain this below because I mean this trips some people up. There's a little rule in modulo arithmetic about this. Okay, and then if we're at the last index 4, well, 4 plus 1 modulo 5 equals 0. Right, like I said, if we see if the modulo expression returns that 0 index, we know the buffer's full. Okay, now this is the part up above, right, the 2 asterisks. So it's important to remember when the result, right, is smaller than the divisor, modulo doesn't do anything, right? It simply returns the number as is, right? So 3 modulo 5 is going to return 3. 2 modulo 5 is going to return 2. 4 modulo 5 is going to return 4. 5 modulo 5 is going to return 0. Right? You see what I mean? So if the value is less, if the left-hand side value is less than the right-hand side value on the modulo operator, you're just going to get that left-hand side value. Okay? So that's what this is doing. Okay? And that's just how modulo arithmetic works. All right? Now, what problems do they solve? Okay, so like I said earlier, right? So they're used a lot in like embedded systems, networking and applications, embedded in real-time systems. So and so they're used in systems where you need bounded memory usage and efficient FIFO data handling, right? And so bounded memory usage means that you just know, right? Like you set something with a set of memory, and that's all it has, right? It's bounded. It's never going to break out of those bounds that you set it in terms of its memory consumption, right? So efficient data streaming. Okay, so the issue is handling a continuous stream of data without dynamically resizing the memory, right? And so a ring buffer ensures that you use a fixed amount of memory while efficiently managing old and new data, right? So imagine packets, right, coming into a NIC, then they need to be processed, right? That needs to happen very efficiently and very fast. And then low latency systems, right? So the issue with these is dynamically allocating memory can introduce delays in systems where performance is critical, right? And so ring buffers avoid memory allocation by making them ideal for low latency environments. And then, there's also the optional functionality of overwriting old data. And so, you see this used in logs, right? Because logs, you only want logs to get to a certain size before you start overwriting the old logs. So they're really good for that kind of thing, okay? Now, the core functionality that we're going to implement is adding data, removing data, checking if it's full, and then checking if it's empty, okay? We get into some big O down here, and you'll see that it's it's constant time, at the head and tail, and then also direct access by index, and then it's fixed capacity, so you don't really have to worry. You're dictating its memory footprint, so you really don't need to worry about that, right? Whereas with dynamic arrays and linked list, they grow, right? They're dynamic. So as you can see, all the core functionalities of the ring buffer operate at constant time, right? So the operation is completed in a single step, regardless of how many elements exist, right? And so this, you guys have heard me talk about my rules of thumb when it comes to big O. And so this is kind of my rule of thumb when it comes to identifying constant time, right? So if what you're doing is completed in a single step, regardless of however many elements exist, you're dealing in constant time, right? So here, push, NQ, push is often called NQ, pop is often called DQ, okay? So the new item is always placed at the head, right? And the head is updated using modular arithmetic. So there's no shifting or resizing there. And then also at the tail, right? The item is always removed from the tail, and tail is updated using modular arithmetic. There's no searching or shifting. And then, you're checking if it's empty is a single comparison between head and tail, and then full is a single arithmetic operation and comparison, right? The modulo bit. So super efficient when it comes to operating within these confines, right? Now, with push, we're always inserting at head, right? And then moving head is just one arithmetic operation. So this makes it so pushing a new item is the same whether the buffer has 1 element or 1 million elements. Now, you'll see up here, where did I put it? So, I don't see where I mentioned this, but yeah, so the dynamic array, I wanted to call this out. So a dynamic array is what we call amortized. It is constant time on most insertions, right? And so you'll see this term amortized, and so I wanted to explain it to you. So when we say constant time amortized for a dynamic array, it means that most insertions take constant time, but occasionally an insertion takes longer due to resizing. And so, but ring buffers, they never resize, right? So imagine a parking lot that holds 100 cars. So in the ring buffer lot, the lot holds exactly 100 cars and no one else can come in unless someone leaves, right? However, the dynamic array, so think about this, right? So the lot, it automatically expands when it fills up by a fixed amount, right? It's not, when the 100th car arrives, you don't open up 101, right? You double it. And so, and this takes time. It takes linear time, right? But it happens only on occasion, right? So for most cars, parking is instant, but once in a while there's a delay, right? And this is why it's called amortized constant time, because over time the cost balances out, like like in finance, and so with POP, we're always removing at the tail, okay? And moving tail is also just one arithmetic operation. Right, and so this is the difference between a dynamic array, which would require shifting elements, which is a linear operation, right? So when that dynamic array gets full, then it's going to go from constant time to linear when it resizes, right, or when it shifts. So that's why a little bit of a caveat, right, when it comes to dynamic arrays. Now, real world applications. Okay, so like I said earlier, ring buffers commonly used in networking to handle data transmission efficiently. Network buffers manage incoming and outgoing data packages, ensuring the smooth flow of data and preventing packet loss, right, from congestion. And then ring buffers are used and the reason that ring buffers are used in these situations is because like efficient data streaming, so incoming network packages, packets, they arrive continuously, and so a ring buffer efficiently queues packets for processing. And then like we talked about, right, fixed memory usage, it keeps memory usage constant, low latency handling, so in high speed network, right, so dynamically allocating memory for each package, it's just too slow, right, it ain't gonna work. And so a ring buffer allows for those really fast insertions and removals. And that also leads to prevention of packet loss. Right, and so consider a situation where you're building a router or a NIC that handles incoming network packets, right? So in a real life network, packets arrive at unpredictable speeds, and they have to be queued for processing, right? And so a ring buffer stores these packets before they are processed by the application. Now this is where you have to start, and a lot of students ask me about this, and we actually get to some common questions that students, because I've taught this a lot, and this is one of the common things, right, is this idea that, like it seems like you'd have to build this huge ring buffer to make it, all these accounts and everything, and and balancing. So the trick is really, you have to do kind of some profiling when it comes to ring buffers, because you kind of have to balance the size of the buffer versus how fast you need processing, right? So if you want faster processing, you're going to have smaller buffers, right? And so, there's this, when we talk about it, I'm talking about it a little bit later, but there's a balance between how big the buffer is versus how fast you need it to process, okay? So let's talk about this networking thing, right? So when packets arrive from the network, it's stored in head, right? And then the head pointer moves forward, like we've talked about. If the buffer's full, the new packets are dropped, right? Similar to real-world networking, right? When the packets are processed by the application retrieves packets from tail, and the tail pointer moves forward. If the buffer's empty, then there's no packets in there, okay? So mapping this to real-world networking. So incoming packets are queued. Okay, so packets arrive very quickly, and a ring buffer prevents data loss by efficiently queuing them. All right, so this would be like an in-queue packet function, so packets arriving from the network. And then the packets are processed in FIFO order. Okay, so the application processes packets in the order they arrived. Just think of an operating system or a switch, right? And so the dequeuing operation ensures FIFO behavior, just like real networking stacks, right? Packets are being processed. And then the overriding old data, right? So in some network applications, old packets are overwritten when the buffer is full. And then of course, like I said a few times, you can modify the code to overwrite the oldest packet instead of rejecting new packets. That functionality really depends on your application, right? Like if you want to immediately drop packets, or if you want, or drop data, it's not necessarily packets. If you want to drop data and ensure that your data is processed in order, or you're okay with new data coming in and overriding the old data, right? So it really just depends on, you can see, right? It just really depends on your problem, like how you need to process things. Now, common questions about ring buffers, okay? So I've taught a number of these classes, right? And these are some commonly asked questions that I've received from past students about these data structures. I think this is really good to add. I think some of my students have had some really good questions, and so I just included this in here instead of thinking about it, right? So, like I said earlier, right, about this assumption that ring buffers need to be like huge. This is something that students have a problem with, right? So packets arrive really quickly on a network. It seems like a ring buffer would need to be really big in some cases, right? Now, so the size of the ring buffer depends, like I said, right? It depends on the rate of packet arrival versus processing speed. And so, you guys know I don't. You guys know I just type and I don't edit. You should know this by now. So a large buffer is needed, right, if packets arrive faster than they can be processed, right? Like in burst traffic. Like you need to be like, okay, well, you got all these packets stored up, and you want to queue them and process them, right? So you need a big enough buffer to handle that bursty traffic, so that it can store those packets, and then it has time to process them, right? And right, and so obviously you need to queue packets longer before processing them, right? So this is if you have more tolerance for latency. So as you'll see here, man, these things are not big. I mean, things, especially things traveling across the network, they're in very small sizes. So in high-speed switches and routers, large ring buffers are used, but we're still only talking about like 128 kilobytes, and maybe some more. To handle these bursty traffic, right? Now, low latency applications like real-time audio, like I said, right, if you want faster processing, you use smaller buffers, right? And then we're only talking about like 512 bytes, right, to minimize processing delay, okay? And so kind of lay it out for you here, how it do. And so, yeah, so you need a larger buffer for certain networking applications because the incoming traffic is unpredictable. And you need large buffers to handle those sudden spikes. And so if you're receiving data in bursts, and if the packets arrive faster than they can be processed, a small buffer, it'll overflow, right? And you'll get packet loss. And so a larger buffer can allow you to hold more of those, all right? And so this kind of goes into a little bit more about, small versus large buffers and when you would want to use them. But hopefully that makes sense. Okay? Now, and then, so this kind of relates to the first question, right? So if a ring buffer needs to be big, doesn't that mean its memory footprint can get out of hand? It could, but ring buffers, it's predictable memory usage, man. That's what these are all about, which is better than these dynamically growing structures, right? So if a large buffer is required, it's a trade-off for performance, right? So audio processing usually uses smaller buffers to reduce, that latency. And then high-speed networking uses large buffers to prevent packet loss because you want to be able to process all those packets. And like here, man, like it's all about monitoring, right? You just want to implement it, and you want to test it, and then you kind of want to tune it based on the results of your metric. This is really one of those data structures where you're going to implement it into your problem, and then you're going to kind of do testing to ensure if it's running the way that you want it to. Now, I kind of get into it a little bit here. I think this is a good opportunity to kind of talk about concurrency a little bit if you guys aren't familiar with it, okay, and thread safety. So are ring buffers thread safe, and can they be used in a concurrent system? This is something, students ask. And they're not automatically safe, right? But you can make them thread safe by using sync primitives, right? So like mutexes and blocks and things like that, or atomic variables. So single-threaded ring buffers work good in single producer, single consumer situations. I was in rare form on this one. And so multi-threaded situations, they require syncing, right? And obviously, if you know about, everyone really pushes lock-free buffers, man. And multi-threading and like high-performance logging, real-time processing, OS kernel buffers. The thing is, guys, like don't don't believe that, oh man, locks, everything needs to be lock free. No, it doesn't, dude. Like I'm going to get into that a little bit, because I hear people people don't really understand like threading and concurrency a lot of times, and it's very easy to over engineer these systems. Okay, so that's kind of what I want to talk about a little bit. Okay, so let's take a look at this code, right? So first we are going to insert arc and mutex from the sync crate, and then a mutex is what makes the buffer thread safe, right? So it places a lock on the data, and basically it makes sure that only one thread can modify the data at a time, right? So the mutex basically, so when a thread wants to operate on the data inside of the buffer, basically it goes in and it locks the door behind it, and when it finishes its work, it unlocks that door, and then another thread is able to come in and grab the lock and lock it, right? And that's kind of what it does. And so, and then ARC, atomic resource counter, it ensures that multiple threads can share ownership of the data safely, right? And with Rust ownership rules, right? It just makes sure that the threads play nicely. Okay, and then we get thread up here, from the standard library, and this gives us the ability to be able to spawn, right, new threads. Okay, and so then we see here, right, so we have our ring buffer with a capacity of 10, and we wrap it in a mutex, and then we also wrap it in an arc, right? And so and once again, so mutex ensures that only one thread can access the data, and ARC basically ensures that that shared ownership safety. Okay, and then we clone ARC, right? So you'll see up here we do ARC clone buffer, and so what this does is this gives each thread its own reference to the mutex and the data inside the buffer, right? And so then when we move our reference in to spawn, we move the reference buffer clone into spawn, right? We place a lock on it, right, using lock. And then once the thread completes its work, the lock is dropped and a new thread is allowed to operate on the buffer, right? So right here, it locks it, it does its task, and then it unlocks it, and then that's what unwrap is doing. It's getting rid of the lock, and then a new thread can come in and do what it wants to do. Okay, now it's important to remember that it's not the data structure itself that's being locked, right? It's the reference to its data. Right, so this matters because mutex locks access to the data, right? Not the data structure itself. The data inside the mutex is still mutable and shared, its only access to it is controlled, right? And so an ARC does not hold the data directly, right? It holds a reference to the mutex, which manages access, right? So notice we got our ring buffer with 10 wrapped in mutex, wrapped in ARC. So we see that inside ARC is the mutex, which wraps the ring buffer. So ARC is actually giving us a reference to the mutex, which holds the key to accessing the data. Okay. Now here, buffer clone.lock, right here, this locks access to the ring buffer inside the mutex, but the ARC itself is still freely cloned, right? And so the ARC is not locked. Multiple threads can still hold reference. The mutex wrapper itself is not locked, only the access to its internal data, right? And so once again, think of these mutexes as doors, right? So the data is inside a room, the mutex, multiple threads have keys, ARC, only one thread can open the door at a time, right? Locking the mutex, and then other threads gotta wait until the door is unlocked, all right? So that thread goes in there, locks the door behind it, does its work, unlocks the door, hands the key to the next one, and they do the same thing, all right? And so you have a bunch of threads that have that own references to the mutex, but only one can go in at a time, right? Instead of mutex, you can use atomic pointers and counters for a lock-free ring buffer. And like I said, guys, always don't try to implement lock-free. It really depends on your situation. A lot of times, man, you're going to have, because implementing lock-free concurrency, it can be complicated. Like it's not complicated, it can be very difficult to reason about, because there's just a lot going on with the threads, and it's hard to keep straight the operations that they're doing in a completely lock-free environment, right? And so a lot of times, man, working with mutexes is a lot simpler, and if you do not need the benefits that come along from implementing a lock-free solution, you should really use a mutex, right? So unless you really need these lock-free data structures, implementing a mutex makes these things a lot easier to reason about, and it's very easy to keep track of what the threads are doing. So, just wanted to kind of mention that. And I'm going to actually have a whole series on concurrency in Rust. I'm going to talk about Tokio. I'm going to talk about all this stuff, right? Like deep level, like systems design and programming and stuff. So there'll be videos soon about concurrency, multi-threading, and all that. Okay. Now, are ring buffers a good solution for any situation where you need fixed size queuing and processing? And I go, students are always looking for like silver bullets, and there isn't one, right, man? That's why you got to know this stuff, dude, because you got to know how to solve the problems, right? Like there is no silver bullet for this. This is why we have so many algorithms and data structures, right? And so, yeah, they're good, but only if you need fixed size storage, or that is acceptable, right? You need FIFO ordering. You need predictable memory. That's when you would use it, right? So like GPUs reading commands using a ring buffer to prevent bottlenecks, right? Or audio buffers using for real-time playback, right? And so like imagine like you're in a video game and you hit the space bar and the dude jumps, right? You want that to be immediate. You don't want to hit the space bar and then have a 500 millisecond delay and then the guy jump, right? You want it to be immediate. And so that's a situation where you would want something, like a ring buffer, super fast real-time processing. Okay, guys. Well, that's it for this one. I hope this all makes sense. If it not, hit me up. Let me know. I'm here. I'll explain it to you. Help each other out in the comments. Ask those respectable questions to get respectable answers. And I'll see you in the implementation video. All right, guys.